Okay, so this is a brief overview of the Messelson and Stahl experiment. And what they did is they were looking for the evidence for replication. So don't forget that a bit of background on this is that in 1953, Watson and Crick discovered DNA, the structure of DNA. Once this structure of DNA was discovered, this double helix, the scientific community began to wonder how DNA replicated itself. And so there was two main hypotheses on how DNA replicated itself. There was another one as well, but we're just going to talk about the two main ones. And that's going to be, was it conserved? Or semi-conserved? So what do we mean by this? So if we have a look at the conservative replication theory, what we see is we see two strands of DNA, and when they are replicated, those two strands, the parent strands of the DNA, stay together, and the two newly synthesized strands of DNA join together. So that was one theory. The other theory that you're more familiar with is the semi-conservative replication theory. So the semi-conservative replication theory states that if you have your parent DNA strands and they are replicated, that you have one parent DNA strand conserved for each replication, and the newly synthesized strand joins the parent strand. So you conserve one parent strand, and you synthesize and join one new strand to the old parent strand. So Messelson and Stahl's experiment wanted to prove the type of the replication that occurred. So let's put that in real quick. And indeed, they did prove that the replication, the type of replication that occurred, was semi-conservative. So the purpose of the experiment was to prove the type of DNA replication that occurred. So let's do a quick background information on this. You need to recall that DNA has a lot of nitrogen in it because it has a lot of nitrogenous bases. So if I just take my quick a monomer of DNA. So what do we have? Just to refresh your memory, not that you need it because you all know how to do this by now really well, but this piece right here, these are my nitrogenous bases. This is my A or T or C or G. Yep. So my purines and pyrimidines have a lot of nitrogens in them. The next thing you need to know is nitrogen, like carbon, like hydrogen, yeah, like phosphorus, like sulfur, nitrogen has an isotope. So the normal nitrogen that we see is N14. There's an isotope of nitrogen that's N15. So a couple of things. One, we know that N15 is radioactive. The other thing we know about this N15 is that it's heavier than N14. It has an extra neutron in it, so it's by definition has a bit more mass, so it's heavier. Okay. The third thing you need to know is if I take bacteria and I grow it in a medium, in order for this bacteria to replicate, to grow and reproduce, it needs to have nutrients in that medium. So the growth medium for bacteria contains sugars and it contains vitamins and nutrients, but it also contains nitrogens. Because the bacteria need these nitrogens in order for bacteria to grow and duplicate. They need to be able to make the monomers of DNA. So of course it would have phosphorus in there, anything that it needed, sugars, anything it needed to make the necessary components for cell division. And one of the things it needs is nitrogens. So if I grow nitrogen in the various types of, if I grow bacteria in the various types of nitrogen, then I can follow them. So what does that mean? That means that bacteria grown in N14 will be lighter than bacteria grown in N15. Okay, you might want to get a piece of paper and jot down these notes as we go. So we said that G is the generation, how many rounds of DNA replication or cell division have occurred. So when we start at G0, this is our starting point. Here what they did is they grew all of the bacteria in the N15 heavy media. And what this does is it allows the DNA to incorporate this heavy nitrogen. And so when we look at splitting this up, we look at our DNA, and what we have for this is all of our DNA is going to be heavy. So all of our DNA, when we look at the double strands, it's going to be like this. And if we centrifuge this heavy-stranded DNA, what we see is in our centrifuge, as we're separating it out by size, what we see is a single band of DNA only. And it's very low in the centrifuge too. And that's because it's being separated out by size, and it's heavy, so it's sinking to the bottom. So 100% of our DNA is in 15 for one strand and in 15 for the second strand. So 100% of our DNA is heavy DNA in both strands. So then what they did is they stopped this, and then they transferred this into a growth media that was N14. So the growth media only had N14, non-heavy nitrogen. The bacteria that we're looking at, by the way, is just E. coli. Okay, so when they did this, the results they got were one heavy strand of DNA and one light strand of DNA. And they stopped it after one round of division, so one set of DNA replication. Then they centrifuged this, and when they centrifuged it, they saw one band, and the band was above the N15 heavy band. So they got one band. Well, we can leave it as purple. But it was at a higher position. Then indicating that 100% of the DNA was in 15 in 14. So 100% of that DNA was heterozygous, basically. You had an old and a new, a new and an old. So then what they did is they continued to let this DNA grow, again, in growth media that was not heavy, N14 media. And what did they find? When they did this, again, your DNA is going to split, and this is going to split. So what do we see? We see one old here, and now one old here, and then new, I shouldn't say old, I should say parent copy, and new. So now what they did is they centrifuged that. And what they got when they centrifuged that was two bands. One was at the same place as our previous band, and one was higher up. So what they have is they have two bands. 50% is in 14 in 14, and 50% is in 15 in 14. And indeed, when you look at this DNA, that's what you're seeing. This is 50% in 14 in 15, and then you have 50% in 14 in 14. So then they grew it one more time, and they grew it in non-heavy media. So let's do this again. So when we look here, and we draw out our parent strands, what we see is we have one parent strand within 15, and then all the other parent strands are going to be in 14, and then the newly synthesized strand is also in 14. And what you see this time, when you centrifuge this information, or this DNA, is again, you see two bands. But what you're seeing is you're seeing a lighter band here where you have the mixture and a heavier band where you have the N14, N14. So what you have is you have two bands. 75% is N14, N14, and 25% is N15, N14. So this was definitive proof that replication was semi-conservative. And here's why. If replication had been conservative, what you would have seen is you would have seen this. That's your first N15 round. Then you would have seen for G1, because this was our G0, let me mark these down for you, G0, and this is G1. So if I looked at my centrifuge tubes, G0 with just N15 would have been here. And if it were conservative, yeah, if it were this model right here, you would have seen two bands at G1, because this band would have been N14, N14, and this band would have been N15, N15. But in G1, that's not what they got. What they got in G1 was one band. There's our G1, one band. 100% of that DNA was N15, N14. It was mixed, so it's semi-conservative. So because they got this band here in G1, they were able to disprove the conservative model for DNA replication and prove the semi-conservative model for DNA replication. I hope that was helpful.